Okay, cool. All right. Hey guys, it's me doing a beginner lecture. It's because David couldn't make it, so I'm just going to do it. But today we're going to be going over a LeetCode problem called network delay time. This has to do with graphs, which is what we've been covering, so it makes perfect sense. Let me get the problem open. All right, cool. So I'm going to read the problem. It says you are given a network of n nodes. So we have n nodes labeled from 1 to n. So I guess I can write that as well. Labeled from 1 to n. There we go. You're also given times, a list of travel times as directed edges where, blah, 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 and W of I is the time it takes for a signal to travel from source to target. So each and every single one of these nodes, they will have a time. Wow, I already know how to spell. We'll have a time from U to V. So if you know anything about graphs, you know we like to call a node U and then one of its neighbors V. So basically what this is saying right here is that this is a directed weighted graph. So for example, we have this node, this one, this is 1, this is 2. Let's also add a third actually. This is 3. From 1 to 2, it is directed, and it has a time, let's say, of 1 second. So it takes, let's say, a signal to go from the first node to the second node, 1 second to travel. Then there we go, like that. And then from 1 to 3, it takes 2 seconds. So just by looking at this graph, I want to basically clear up what this question is asking. Let me actually read the final paragraph. It says, we will send a signal from a given node K start from node K. So we are given a node K, and that's the first one we want to look at. That's where we start. And what we're supposed to return is the time it takes for all the n nodes to receive the signal. So let's say here for this problem that we're discussing, let's say K is equal to 1. If K was equal to 1, how long would it take for every single node to be reached or to receive that signal? Well, let's look at it. If K is 1, that means we start here. In 1 second, we can reach 2. Then in 2 seconds, we can reach 3. So the maximum time it takes to reach every single node is 2 seconds, right? Let's say we added another one. How about now? How long would it take to reach every single node if K is still in 1? 6. Is there a better path that we can take?
Oh, okay.
Yeah.
I guess 2.
Exactly, 2. So we can go from 1 to 2, and then 2 to 4. That will give us, oh, that looks like 3. And that will give us an answer of 2. So instead of going, let's think about it this way. In 1 second, we can already reach 2, and we can reach halfway to 3. Then another second, we can reach 4, and then we can fully reach 3. Did that part make sense? Yeah? Okay, cool. All right. So that way, we're able to reach both of these nodes by the time we actually reach 3. That's why the answer is 2. That's the shortest times it takes to reach all nodes. I think they say here maximum time. No, they said return the time it takes for all the end nodes to receive the signal. Cool. Now let's say, let's change this graph a little bit. So far we went over the description of the problem. We've also seen a couple of examples, well actually only one example. But now let's try to do a couple more examples so we can really drill what the problem is asking us and see if we can figure out a pattern. Okay, so K doesn't change. Our starting node is still this first one. But now how long would it take for us to reach every single node? 3, okay. Now why would it be 3?
You go 1, 3, 4, and then 1, 2.
So 1, 3.
Same time, 2, 3.
So from 3, can we reach 4?
Yeah.
We could?
Oh, okay. No, wait, I wasn't looking at the arrow. Okay, no. So we can't reach 4.
Exactly. So we can never reach the 4th node. We can reach 3, and we can obviously reach 2 as well. That would take 1 second to reach both of them. But we can never reach 4. When this is the case, when it's not possible to reach every single node or to reach n nodes for the signal to reach n nodes, instead let's just return -1. So now we know both caveats, whether we could or could not. Let's say this was different though. Let's say if this arrow, instead of going from 4 to 3, let's say the arrow goes from 3 to 4. And it still has a weight of 2. How long would it take now? Yeah, 3. So now the answer would be 3. Because we go 1, 3, then 4. Perfect. So now let's do a little bit of a bigger graph. And let's go a little bit slower on this one. Cool, okay. Let's change this to another 2. All right, so what's the answer to this? Oh, if you actually do, I'll be impressed because that was just a joke.
I think it's not bad. Good.
Okay, all right, let's see. So obviously we start at 1, right? Because that's where K is. That's our starting source. Then from 1, we get to choose either go to 2 or 4. We're obviously going to choose 2. It will travel, the signal will reach 2 quicker. So we know we've reached 1, we've reached 2. Now how long would it take to go from 2 to 3? It's always 4, but in total, for the signal to get from 1 to 2 to 3, it's 5 exactly. So we want to keep that in mind and carry that. So at this point, we can get to 3 in 5 seconds or 4 in 5 seconds. Let's just go ahead and choose 3.
Why do you choose 3?
I don't know. They both have the same weight. We could have choose either one.
But wouldn't you prefer to reach more nodes in the same time?
So we're still going to hit this 4. But the first one that we want to choose is 3. Because for example, now it's 5, right? But from 3, we can reach other nodes. And that weight will be greater than 5. So we're for sure going to do 4 next.
Okay.
You know what I mean? Did that make sense?
Okay.
Because they're all positive weights. The time it takes is all positive. If I had chosen 4 first, I now have the option to reach 3 for 7 seconds, right? Or to reach 5 for another 7, or to go to 3 for 5. So I'm going to do 3. Either way, both of them will be hit. It's just like the first one that I chose just was 3. Either way, they were both. Because to get to 3, it took 5, right? To get to add the other node from 3 is gonna cost us more than 5. And then 4 was exactly 5, so we're for sure gonna hit that one. Make sense? It's okay.
Go back to 1, or I'm just trying to figure out the algorithm.
Yeah. So this carry that we're doing, how from 1 to 2 is 1, but then 2 to 3 it's 5. That's gonna be extremely important. And keep in mind that we have multiple routes, right? We were decided between 3 or 5. Or let's go back a little further and we were deciding between visiting 2 or 4, right? We chose the one that had the less weight. So that's something very important that might tell us what data structure we might want to use. Yeah. So we've seen 3 and 4. We saw 3 first and then we went to 4. And now we can reach 5 for a cost of 7, or 5 for a cost of 6. Obviously, we're choose 6. We're going to go 1, 2, 3, 5 for 6, instead of doing 1, 4, 5 for 7. And then from here, we don't really have an option. We want to do this one for 9, because 6, 1, 2, 3, 5, 6, plus 3 is 9. And we visited all nodes, so the answer should be 9, I believe.
That's the minimum time to read.
All nodes, yeah. So let's break it down. Okay, so let's break it down. We obviously starting off at 1 for a weight of 0, right? Can they see that? They could, yeah. Right. So let's say we pop it, all right? Or we take this route that we should take. So now 1 is out of there. But before we actually pop it, we pop it and now we're currently holding on to it. We want to look at all its adjacent nodes. So we can get to 2. And for what cost can we get to 2? 1 plus the cost of 1, right? So that's just going to be 1. So we can get to 2 for a cost of 1, or 4 for a cost of 5. So because those are its neighbors. So now we're done with 1. Now which one do we want to look at? We want to look at 2 because we'll get there quicker, right? Now intuitively, that makes sense because if we can get to 1 node quicker, from that node we might be able to get to other nodes quicker. So let's now pop 2. Now let's look at the neighbors of 2, right? And now what would that be? 3 for a cost of what? 5. Yeah, 3 for a cost of 5.
Which is the one that I popped plus the cost.
Exactly. The cost I took, for the one you popped, the cost I took to that one that you popped, plus the weight of the edge to go to its neighbor. So from here, we can pop either. You want to do 4 or do you want to do 3?
The first in the list, which is
4. Okay, so you want to do it by a time based. Okay, so let's pop 4. Now what are we going to add?
3 and 5. Well, 3 is already created. So we have to.
So we
choose.
Wait, we have to what?
Choose.
We can add it again, right? And when we're popping, we're going to choose the 3 that had the lowest weight. And if we ever choose 3 again, we just check, have we seen this node? Have we visited this node? If we have, don't look at its neighbors. Or don't reconsider it. So let's go with that scenario. Let's add it just so I can show what I mean. So we're going to reach 3 from 4 for a cost of what?
5 plus 2.
Yeah. And then which one else can we reach? 4? I mean 5?
5.
Yeah. For a cost of what?
7.
Yeah, exact same thing. So now we want to look at this list. We're done with 4. Now we want to look at this list. And we see that 3 is one with the lowest weight. So we want to take that one. We want to consider that one. Now from 3, let's look at its neighbors. In this case, it's only 5. So we want to do 5. Take this weight that it took to get to 3, plus this weight of the edge. Combine them, and now you have 6. From here, do the exact same thing repeatedly. We choose 5. It's one with the lowest weight in the list. Add its neighbor. In this case, it's only 6.
How did you cancel 3? I mean, we still kind of have a 3.
Yeah, we still do have a 3, but remember we're looking at the
Okay.
The weight.
Like we ordered when 5 came in.
huh?
When 5 came in, like, why do we have 2 5s?
Because from 4 we can get to 5, and then from 3 we can also get to 5.
Okay. So those 3 and 5 that we have, we won't meet them?
No,
Okay.
you see why later. Well, actually right now. So from 5 we can get to 6 for a cost of 9, right? Now when we pop, we're going to choose 3. We choose it, and then we check, have we visited 3? Is a 3 already in our list or in our set, whatever? And it's going to return true because we have previously visited. Therefore, we don't look at its neighbors again, and we just ignore this. We're going to pop one more time. We choose 5. Same thing with 5. We check if we visited it, which we have. Therefore, we don't continue. Never talk to me again.
Really sorry. There was a train and it was there for 20 minutes.
A lot of people left.
Yeah, everyone left.
Everyone left?
Hermes and I forgot his friend's name, but they left.
Well, Hermes kind of just,
Yeah, he always leaves, but still, he got pretty mad.
he got pretty mad?
Yeah.
The professor came and was like,
Yeah, Geary came. He's like, I'm excited for this.
Dude, I'm really sorry.
Dude.
I did not anticipate that. on
FIU
purpose.
president, you're being expelled.
Okay, well, you know what? Now I know you're in control.
Yeah, no, it's fine. I'm not doing the extras because I wasn't prepared, so I'm just doing this.
I'm gonna do credits. I should do credits. On the road.
I don't think you have time to teach today.
no, wait, no, okay. So what are you doing then, though? Like, is there a name for this?
Priority queue.
Huh?
This is a priority queue.
Or a menu.
But the algorithm, I mean, I guess that's a data structure.
Yeah.
But what's like the algorithm?
Oh, it's just adding every edge to the heap. Yeah, you do Python, so let's call it heap. To the heap, and then continuously choosing, popping from that heap, the node with the lowest edge rate. So that's why we're doing this.
That's not the extra, that's not.
So yeah, that's what I was going to tie in later. But for now, I was just trying to like get your head around how it works, and then I was going to let you know, oh, this is Dijkstra's, and you're going to be returning the path that had the largest weight, which I'll get into later. Don't worry. So we got rid of these 3s and 5s, which because they were repeated, and we had already visited 3 and 5. Now the last one is just 6 and 9, which we pop. It has no neighbors, so we're done with this. Now, okay. Now, to return the answer, we want to have kept track of these edge weights. So for every time we visited a node, kept track how long it took to visit it. So let's say we have a hash map with 1, it took 0 seconds. When we got to 2, it took us 1 second. When it got to 3, it took us 5 seconds, not 7. It took us 5 because we want the minimum. And remember these, we instantly saw that we repeated it, that we've already seen this node, so we didn't do any computation at all. Then 4, we saw at 5 seconds. Yeah. Then 5, we saw at 6 seconds. And then 6, we saw at 9 seconds. This is every node in our list. And then this is every, the time that we saw that node. We choose the maximum of these times, which in this case is 9, and that's what we return as our answer. Does that part make sense?
Yeah. But couldn't we have used the heap
Huh?
to determine that?
Yeah. So let's say if this, for example, the 3 and 5, right? We knew they were repeated, so we completely ignored it. If every time we pop from the heap, we do like answer is equal to 0. No, actually, I think this is how I did in my code. I forgot. Answer is equal to -1. No, I don't think this is how I did in my code. Answer is equal to -1. And every time we pop from this heap, we do max between answer and this weight. For example, max between -1 and 0 is going to set to 0, then 0 and 1 and stuff like that. So that's how we get this 9. And we're not going to get these 7s because remember, we have already seen that node, so we ignore it. So yeah, you could have either done it that way or this way. Something else to keep in mind is that if we have not visited every single node in the graph, we need to return -1. How can you do that? Well, you can do it with this. Taking the keys, the length of the keys should equal n. Should equal n. If it does not equal n, return -1. You can also do it something like this as well with answer. Do like node count. Set it equal to 0. Every time you see one, increment it. And then if node count does not equal n, return -1. So that's how we can take care of those caveats.
So here, the last node that we put in the queue, the current queue, is it coincidence that it is the largest time, or the greatest time?
If it's the last node you get to, that's what you want to know.
Yeah, like is the last thing that I put in the queue always the answer?
No.
Or not necessarily?
Not put in the queue, no. The one with the greatest. Yeah.
Let's say we have this, right? 6, let's say 6 goes back to 3 for a weight of 4. The last thing you're going to add is 9 plus 4 is 13. Right? But you're going to pop this, you're going to see that 3 has already been repeated. This was technically the last thing you popped, but it's not your answer. So do you see how this falls or how this works out? Is there like any questions you have for this? Or do you understand like pretty much how the algorithm will work?
Want me to write the code?
Oh yeah, if you want, you could write the code.
Yeah.
But let me explain one more thing. So simple when we have like the graph and everything, right? But they make our life a little bit harder. This is how we wrote it out, and this is how the input is represented. But how the input really looks like is a list of lists. So they might give you something like this. And then, of course, they will also give you, what do they call this, times. They will give you n. In this case, n is 3, I believe. No, it's 4. And they give you k, which is your starting node. So is it okay if I erase this? Yeah, all right. Do you have any questions before I erase it? No? Okay. So this is your input. It's 3 inputs. You have times, which is a list of integers. You have n, which is the number of nodes. And you have k, which is your starting node. What does this represent? It represents this graph. It represents exactly that graph. So how can we read this? Do you want to?
The index is the node.
The what?
So like index 0 goes
Yes.
to
Yes.
node 2,
Yes.
1, and 1.
Yes. So that's
One is like itself.
Yeah.
so think of this as U, node we're currently looking at, V, its neighbor, and then W, the weight of the edge.
Okay.
So yeah, you pretty much got it. 2 goes to 1, which is a neighbor, for a edge weight of 1. 2 goes to 3 for an edge weight of 1. And then 3 goes to 4 for edge weight of 1. 3 goes to 4, edge weight of 1. So with this, how can you represent a graph with this? How do you want to work with this input and set it up so it's a little bit easier for yourself? What's 2 data structures, I guess? Not data structures.
Yeah.
Really? We call them data structures?
Yeah, data type.
Data, whatever, let's just say data structure. What data structures will you use to represent a graph?
Adjacency list or matrix? Like
Exactly.
adjacency matrix.
Exactly. Adjacency matrix. Adjacency matrix or adjacency list. You know your n, so it's pretty easy to set up the rows and columns. And then you just want to do at this row, at this column, put this weight. At this row, at this column, put this weight. The way I did it is adjacency list. So at this row, append 1 for a weight of W.
So what did the code?
Hey.
How do you do the weights and the adjacency list?
Yeah, so instead of like 0 or 1 representing where there's a connection or not, you can either do a tuple. That's how I did it for adjacency list. That's how I did it. I put that in this row. So we have 0, 1, 2, and 3. So in row 2, append 1 with a weight of 1. Then at row 2, append 3 with a weight of 1. Close that out. Then at 3, oh, I messed this up. Crap, I messed it up. Okay, you get the point. Let's just erase this, because that's who represented the 3. So that's how I did. Or I think if you're doing a matrix, it's pretty much going to be the same thing. Uh, 0, 1, 0. Yeah. 0, 0, 0, 0. I'm not going to add all the zeros, but you understand there's 2 more. Here, you know there's a connection? Oh, it should be actually here. Should be in both of them. You understand there's a connection, but they both have a weight of 1. If, for example, this had a weight of 3, you can do something like 3 or whatever, wherever it should fall. So instead of being like a binary matrix where 0 represents there's an edge and 1 represents there isn't, it's going to be a matrix that represents the weight of that edge. And then you can figure out the U's and V's just by looking at the rows and column that edge falls under. That part makes sense? Yes, cool. So I talked about high level how the algorithm works. We also figured out how to work with this input to form it in something we've seen before. Now David is going to come and write out the code for it. Huh? Yeah, sure. What do you think? Should we do the blue thing or on the whiteboard? The blue thing? Okay, cool. Let's do that. Yeah, they like the blue thing.
Most of them really again. Like I did not anticipate my commute being
Sorry
that
to
bad.
Gary.
I'm so sorry to Geary,
And Rosenberg.
and I'm gonna say sorry to Joe Biden. I'm gonna say sorry to UN General,
To the Panther Society.
to the Panther Society.
At least you look spiffy.
I did. I chose a very good. I don't know. I just felt like wearing something different about this on Friday.
Looks like something Adrian would wear.
Anyway.
Did you go with him to buy it?
So again, I
that a
am
yes?
really sorry that I got here really late. I did not anticipate my commute to have that many pitfalls. So.
Did I guess it?
So, but basically, I'm gonna write the code, the Python code for this problem, and I'm not gonna answer Lazaro's question because I mean, I don't feel obligated to do so.
When would you like to represent a graph with an adjacency list instead of a matrix or the other way?
If it's sparse or dense.
Right. If there's like a lot of edges, right, and they're really like connected, then it would be useful to use a matrix. But if it's like not that many edges and they only go to specific ones, then you're gonna have like a lot of empty zeros and being useless. You know, say you've got node 1 to 3, right, and that's 0, or
Like if it's a linked list,
yeah.
Or it doesn't have to necessarily be linked list either.
like it looks like it. I'm just like,
Yeah, kind of. Yeah. Kind of like a linked list. If it's like a linked list, then you're gonna have like a whole, like it could be just a diagonal, and everything is 0 and being useless.
so that's when you want to use.
Yeah, when it's a sparse and doesn't have that many edges, adjacency list, because you're saving space.
Okay.
But if it is dense and you find that nice opportunity, then yeah, do use an adjacency matrix. Oh, okay.
So
Wow,
this
that's
is
a
a
lot.
graph, right? Graph is just a mathematical object
Yeah.
of nodes
And edges.
That's it.
All right.
You only have one edge. In this matrix, you would have 15 by 15,
Yeah.
whatever number that is.
There's only going to be one cell that's going to
What number is this?
215.
Is it really 215?
I think it is.
Oh, I think you're right. Okay, hold up.
There's only going to be, it's all zeros in the matrix with just one 7 somewhere.
No, I think you're wrong.
Am I? I mean, if I'm wrong, I'm wrong.
Lazarus,
Wait, what?
Isn't it 225?
Is it 275 or 225? 225.
That makes, okay. So you have
225.
224 zeros and 1 1.
Or 7. All right, I put 7 there.
Oh, you added a weight?
I added a weight. Yeah, so basically at that point an adjacency list is much more useful. But that doesn't mean an adjacency list won't, have its drawbacks too when it comes
Wait, you
to
said
this.
125?
225.
Okay.
225. I said 225. Okay. Well, I like making an adjacency list. Personalmente.
if you don't know if it's going to be sparse or not, you just do it.
I mean, you never know. I think as a rule of thumb, I generally just make an adjacency list, right? So remember, they gave you, is it 3 tuple? So what I would do is, well, let me define the function first and foremost. I don't even care about the self. We got time, and you've got n and k. So you make an adjacency list, right? Just as a rule of thumb. And can they see this, or is this too light? They can't see it. Okay, great. Right? Then I go through time, right? For times, right? So we know that the first tuple, the first number in the tuple is going to be the source, right? So I have to initialize it, right? I'm going to run out of space. So I do this first, right? What this means is that I'm getting the adjacency list of the first, of this source. Get it, or if it's not there, then set it to an empty list, so as to kind of initialize it if it's not already there. Of course, I could do if time 0 not in adjacency list, then adjacency list time 0 equals empty list. You think that might make it simpler?
No.
I'm gonna keep it like that. This
That's
just
in Java as well.
yeah. This is in Java. This would be get or default.
Yeah.
Yeah. Any
Wait,
question?
yeah, you get it.
Do you get this? Do you get it?
If the source does
Okay.
exist,
Yeah. Okay. If the key is in the dictionary, right?
Right, in that case.
Retrieve it. But if it's not in the dictionary, return this empty list. Set it.
So whatever it was.
Yes. Yeah. Yeah. That's basically all it's doing. So now I'm going to.
Oh my god. Use the red one. I'm sorry.
It's fine. It's fine. You know, I'm the one that should be sorry for wasting everyone's time.
Watch this.
I made it in, guys. He's a great. Actually, just do it again. Just do it again. Yo, everybody.
That was good.
He made it in. It went in. Okay. So we're gonna set it or just retrieve it. And what we do, we're gonna add to it, right? It's a list. List dot. No. We're gonna append to it a tuple. What are we gonna append to this adjacency list? Given time 0 is the source.
Time one.
Yeah. Okay. Wait.
Oh, wait. Yeah, a tuple actually.
Yeah.
Time
Mhm.
one
Mm.
and time two.
Okay. Perfect. So we're gonna append I'm gonna continue down here. A tuple being the destination node.
Oh my god, my markers are. Try this one.
I'm gonna just
I think
wear.
this
I'm
one-
gonna wear this one out.
Okay.
I'm gonna wear it out.
I'll
Okay.
probably do a lot for next time.
You got this for free, right? These are the ones that FIU gives
Yeah,
out.
but I don't really like these. I like the Expo ones.
Yeah, Expo ones are really nice. They're clutch. Okay, so you append for this source node. You're gonna append the tuple, the destination node v, and then the weight. Okay, so you've made it, and now here's the Dijkstra part of it. We're gonna make a distance. Well, maybe you can make it a list, right? Did you make it a list?
What?
The distance data structure.
No, I'm pretty sure I did a.
You
hash
did,
map, but
you
you
did a
can do
hash
a
map?
list.
I think you can because it's 1 to n.
Yeah, yeah, for sure.
Okay. But then again, I have to kind of check the length, right?
Yeah, but you can do the length by the keys of the hash map. Can you not?
I mean, yeah, I guess so. I'll just make a hash map where the keys are the nodes.
That is after the for loop.
This is okay. So during the for loop, we're going to keep changing the keys, right? We're going to change the values. So we have to say
Wait, but you want to initialize something.
we do. Yes, we do.
K0.
K equals 0. Oh yeah, yeah. Oh, okay. So we're actually going to make a min heap or a priority queue. They're interchangeable. So in Python, you just make a list, and then you're going to use heap queue. So kind of pretend that I imported the heap queue library. So what do we append to the min heap at first? Okay, what do we append?
Okay.
Okay. So, and what else?
0.
Right. So which one comes first?
Wait.
Yeah. The order doesn't matter.
The heap, you're gonna do it as a list.
Okay, so here's the thing. In Python, right, you make a list, right? There is a heap data structure. But the thing is that Python works on its list, right? So when you heap push, heap pop, you're gonna heapify a list, all right? So since there's only one thing in there, we don't need to do anything min heapy. We're just going to add this, right? And it's important in the order, right? 0, right? So it's k, but we have to put 0 before k. And maybe I will use the green one. Maybe I'm gonna use it now. It's getting bad. Okay, do we get this so far? So we added to it, and since it's the only one, we don't need to heapify it because it's the only one. And when it does heapifying, where's it gonna order it by? Yeah, the first element in its tuples. So it's always gonna. That's why I put the distance. I put it first. Okay. Now we're gonna loop through while min heap. So while the min heap still has elements in it, right? We're gonna pop from it.
For distance, we want to do k0 now. Node k set it equal to 0.
We're actually gonna.
Oh, you do that.
Well, I did it in here.
Oh,
I do it in here. And then
oh, I see.
HQ. So this is the heap Q library from collections. So I didn't put it there, but let's just kind of just say I did. Yeah. So I'm gonna. It's a heap pop. So when a heap pops, it's gonna take the minimum, which is the first one, but it's gonna reheapify it such that the minimum will come at the top again.
I want to ask a question also. Why can we append to our heap with the tuple k comma 0, or does the order there matter? Like here in mean heap dot append, do you think that order matters, or could we also have done k comma 0?
Yes, it does, because I think David said that.
Oh. Sorry.
It's all right.
Ordered by index, by the
I
first
deserve
one.
that, by the way.
Yeah, and what does the first one represent?
What do you mean? Oh, the first one is the distance so far.
Yeah.
The cumulative distance to that node, yeah. Okay.
Yeah, and the cumulative distance to the original, which is k, which is the source, is 0. So, and what are we gonna do? Okay, so here's another check, right? We made the distance, so now we have to check if the node we're in, which I put it here, which is, this is just a number. I mean, that's just like this one right here, right? That's just a number. If node in dist, what do we do? If we already checked that node, right?
I was thinking about the heap by default organizes them from minimum to maximum.
Yeah, so that means, yeah, the minimum is all the way at the head, or at
We pop, we
the,
click on minimum.
yeah, so, and then it's going to get the new one. So it's going to reorder the whole list again in the same structure, just with one less element. So this takes log of n. This one takes log of n. So if we already saw the node, just continue. We're not going to do what we're going to do down here. Okay, does that make sense? Because we already did work on that one. Okay. But if we didn't, then I would say set the distance value of this node to the distance we got. So this is where I set it up, Lazaro. You asked before? Yeah, so I'm going to get k, and it gets 0.
Yeah, you started with k, but I started with the neighbors of k, so that makes sense.
Mm-hmm. Yeah. So, I mean, it's just like another way of doing it.
Yeah, no, yeah, it makes
Yeah,
sense.
it's weird, I know.
No, it's fine.
Mm-hmm. Okay. So where was I? All right. So now, okay. So now what is this? What am I doing? If node is an adjacency list, why do I do that? Why do I want to check that the node is in the adjacency? What does this mean? What does that mean?
There's a node to solve.
Well, that means that in the adjacency list we made, this node goes to other nodes. If it doesn't, then
So like if it has
Yeah.
adjacency.
Yeah, if this is no other node adjacent to this current one we're at, I mean, can just continue, right? You're not really gonna do anything. And if that just so happens to be the last node in your main heap, you're done, right? Does that make sense? Okay. So if it's in there, right? We check for every edge. I wrote the G right? I wrote this, okay. Just making sure. So for every edge in adjacency list of the also, it's for this too, right? So if the key is not in here, then that wouldn't work. So for every edge, so kind of like this, right? So we're going through every one of those. What are we gonna do, right? We want to affect this min heap. What do we want to do to the min heap? Yeah. Yeah, so we want to add the tuples to it, actually. So h cube, right, dot, we're going to push it.
Push it real good.
Okay.
Sorry.
Don't say it again. Right, we're going to push to this min heap, and we're going to push a certain tuple, and I want you to fill in the gaps. What are we pushing to it?
The minimum?
No. Well, I mean, we pop the minimum, but we're going to push something to here. Okay.
Oh, we definitely have to push the adjacent node?
Yeah.
With a certain distance.
Okay. So is that going to be the first or second element in the tuple, the node? Okay. So what's going to be the first one?
That's what I was trying to say.
Yeah.
We need the minimum between the accumulated distance?
Don't worry about
Okay.
that just yet. Okay. Well, what do we know? So definitely we want to include. I'm going to just stand up for a bit. My feet hurt.
But don't you unpack it so it's easier to see?
Actually, maybe you have a point. Okay. So I'm actually going to write it first. So,
You can do it in the for loop, unpacking the for loop.
what do you mean?
Like instead of edge to like U, comma, W.
What do you-
There's a tuple there, right?
Yeah, you're going to add a tuple. Well, I guess. Oh, you know what? I could do. I'm going to write a new variable, and that's going to be the new distance, right? And it's going to be a distance to the current node we're at. We're good on that? We can do that? Okay, so I'm going to say,
So edge represents a tuple, right?
yeah, it's the source and then the weight.
So why
Of
not
that one.
unpack it right there? Like do for U, comma, W in adjacency list node.
I mean, why didn't I unpack it here?
The reason we want to unpack it is because we're going to the position.
I mean, but yeah, but well, hold on.
Okay.
We're gonna worry about that soon. So the distance to V, right? What is the distance to V?
The first edge is 0.
Okay, so edge will be edge 2, right? No, edge 1. So it'll be edge 1. But it's a little bit more than just edge 1. We want to add something to it.
Isn't the position 1 the destination?
Yeah. Well, no, that's the weight.
Okay, yes.
That's the weight. That's the weight up there. Yeah. So V dist is edge 1 plus something else.
Plus whatever was in the adjacency list.
Well, this is what's in the adjacency list.
Okay. I think I meant
Yeah. Okay. So what was
Yeah,
in the heap
right.
before? So the distance, the prior distance. We want to add on to the distance. This value plus plus distance. So this is distance to v, which is the destination node. So we're going to add that. HQ dot heap push, and I'm gonna put it as a tuple. So obviously the first thing we want to put is the distance, right? Because that's how we're going to order this main heap, and of course edge. Okay. You see that, right? We get the distance to v, because that's what we want, because then we're going to use this again, right? After, yeah, to its adjacents. And then we're going to also add edge 0, which is the node itself. Okay, and just keep doing this. This is the whole while loop. And once you finish, what do you want to check, right? What you mentioned before, which is you want to check the length of dist. Why?
You want to what?
The length of dist.
To make sure that, to see if we visited all of them?
Exactly. We want to make sure we visited all of them. So after this is done, if len dist, well, if it's not equal to n, because it's going to be at most n, we return -1. All right? But let's say that this doesn't pass, so what do we return?
We have to find
Yes, we did.
It's not the last one.
No.
Oh, okay.
Well, the heap will be empty by the time this is done. Yeah, because that's what this checks
So
for.
we just have to look at the distances,
Mm-hmm.
check which one is the highest one.
Yeah, because that one was one that took the most amount of time to get to. That's the one where we're like, okay, this means that if this took the longest, we're done with all the ones before.
Okay.
So we return. Okay, now you can't see that.
Be the maximum of the value.
Yeah, I'm gonna stand up. I'm gonna continue writing it up here. You think they can see it? No, they
I
cannot.
have the code on the screen anyway.
Huh?
I have the code on the screen because the markers are pretty hard to see. So I'm like putting the code here.
Okay, yeah. So you get the values of this one. Okay, well, you get the values. Here it's called values. No, scene. I called it dist because it's distances. But you get the values of that and get the max, and that's it. That's how long it takes to get to all of them. Okay, and that's this problem. This is actually a pretty cool problem. There was another one that I really liked that I wanted to talk about.
Maybe next semester.
Maybe next semester we'll go over it, but yeah, that I'm really sorry again that I'm late. This is the last one, and I know you were hoping for this to go off without a hitch, but unforeseen circumstances came my way on my commute. But next semester this won't happen. Like it won't happen at all. Tonight at 7:30, they're gonna showcase the projects at the mobile dev community. So it's in case 138, I believe. Yeah, same building as this one. So please show up. A lot of people worked hard, and they're proud of their projects. So we really appreciate the support giving to the mobile dev community. Wow, it's a mobile dev community. We kind of think redundant. But yeah, outside of that, enjoy your Thanksgiving and I guess Christmas. Well, we're gonna see them. When's our next general?
This Friday. Next Friday.
Next Friday is our next general body meeting. We hope to see you there too. All right. Thank you for attending.